All right, so now we're ready to put together all the Gauss's law stuff, and I want to put something in here that we'll talk a lot more about in Unit 10 when we get to conductors. But one thing that will be very common in when you're doing Gauss's law problems is electric field inside conductors. And we're not going to go into the details now. Really, today I really want to talk about the contents of how to do Gauss's law. So we'll get to that when we talk about more about why this is true. But in a conductor, if you have a conductor, electrons are free to move around. They will move to balance external charges. The end result is that the electric field is zero inside a conductor. At least in what we call this static equilibrium case, which is always the kind of the scenarios we run into with Gauss's law. They will always balance, charges will always move to balance out to make the electric field effectively zero inside a conductor. And that's going to be important because now we're going to apply actually Gauss's law. So Gauss's law, it's a powerful tool that relates the electric flux and the enclosed charge, right? So that was the last two things we talked about. How do we calculate flux? How do we do the charge, or how do we calculate charge from a distribution? And this is where it puts together. Now, notice this integral sign has a circle on it. Okay, so when we do this circle, this is intentional, and you might have saw in the lesson we didn't have that circle in there. It's to indicate that we're doing the flux over a closed surface. Okay, so a closed surface means that it has to contain a volume and it has to be completely sealed. There can't be any openings left. Think of it like a balloon, if it's like more of a circular, or a cylinder, a solid cylinder, but it must enclose a volume of area. Sorry, it needs to enclose a volume in there. Okay, and then we're talking about the flux over the surface of that volume. The charge enclosed is just like we talk about. We're going to create a surface. We're going to calculate the flux that's exiting that surface or entering that surface, and then look at the enclosed charge. And so in principle, this left integral in general is too complicated for us to solve analytically. Not until you do multivariable calculus can you really do this. So the whole idea is we only use Gauss's law when we can pick shapes to make this flux integral very, very simple. Okay, so because in general, you can do these kind of closed surface area integrals, but it does require you to know multivariable calculus, and that's not something you're required to know for AP Physics C, and it's not something we generally would use in a practical sense anyway. Our goal is to shortcut the electric field calculation by applying this rule and by building a surface to where this integral ends up being really easy to do, the flux calculation being very, very simple. Okay, so if we look at the problem solving steps, this is the idea of a problem solving step when you're doing Gauss's law, is first you want to identify the direction of the electric field given a charge distribution. So we want to know this. And the key here is to notice any symmetry that may be occurring. So we're going to focus on that a little bit. Then we're going to pick a closed Gaussian surface. This is really critical. Now, in order for us to calculate the E field very effectively, we want the surface to either go parallel to the electric field so that the flux is zero, or we want the electric field to be perpendicular to the surface so that when you multiply the flux, you just multiply the electric field times the area. You also want the E field to be the same magnitude everywhere along the surface. Okay, so that's going to be super important too, that not only is it perpendicular everywhere, but like we want it to pierce it there, and we want the magnitude to be simple so that the flux integral will then just simply become the electric field times the area. Okay, that's our goal. That's the choice of the Gaussian surface when you're doing that. Then we're going to go through what we talked about before, computing the electric flux, then compute the enclosed charge, and then set them equal to each other like this. It's equal to Q enclosed over epsilon naught. That part is important there. So let's go through some examples so we understand how this kind of operates here. So we have a large infinite sheet that lies in the XY plane. So this extends out in all directions here. So we're just going on. It carries a uniform surface charge density called sigma. So this is a charge density per area. It uses Gauss's law to find expression for the electric field at a point located distant z above the sheet. So first is we have to understand the direction of the electric field here. Okay, and this is where it's tricky, because you might be like, how is it? So first of all, it's definitely pointing away from these positive charges at this point. The question is it like this way, or is it this way, or is it this way, or is it sticking out? How do we know the direction of the electric field? And this is where we use a symmetry argument. Okay, so I know that it's going to point straight up. So let's say it pointed this angled here. Okay, so think of this infinite sheet charge. Let me get a piece of paper real quick. All right. So imagine that this is the infinite sheet charge, and I'm telling you that the electric field points in this direction here. And this sheet extends in all directions here. And I say, let's say it's pointing in this direction. Well, if I were to rotate it, then it would then rotate this way. Does that make sense? But it has to, it's still the same scenario. Like this scenario and this scenario ought to be the same because it's symmetrical. Like if I rotate it, it's still an infinite sheet in all directions, but now it's pointing towards you instead of pointing to the right. Right? So is it pointing towards you or is it pointing to the right? Because I rotated the sheet, so it feels like I got to rotate the electric field, but then like this is the exact same scenario as this because it's infinitely in all directions. So that means it can't have a horizontal component because if it rotated, then I have an inconsistency. Is it pointing this way or is it pointing this way? So that's how I know it's pointing straight up, okay? Like it can't point in another direction because if it did, then it would break symmetry because then it would be like, oh, I rotated it. Now it's pointing this way, but I just said before it's pointing this way because it was the exact same scenario. So that's a symmetry argument. That's the argument we're making in the symmetry. So in this case, we do know that the electric field is pointing upward here. And the other symmetry, it's pointing upward here. So the other symmetry argument we're going to make is to say like, look, is it the same here at any other location at the same height? And that would make sense because if I move it right over here, it's still infinitely charged over here. So like this electric field, when I move it over, okay, cool, exact same thing. But then this scenario, me shifting the sheet over like this, is still having the same electric field pointing up here, right? Because there's no difference, because it's infinite in any direction. So me shifting it shouldn't really actually change anything. And so by that argument, we can say the electric field is the same at any given height. Okay, and so that kind of puts us together into what we're going to do next, which is to say like, okay, cool. So I know that the electric field has the same magnitude at the same height, no matter where we are in there, and I know it's pointing straight up. All of that by symmetry. And that's super important to understand because then, and then we're going to do one more thing, okay? We're going to look at, because I got to create a surface here, and we're going to look at the opposite side over here. If this distance were z, then I know the electric field is pointing this way, and I also know it's the same magnitude, because if I flip it upside down, it should be the exact same thing, right? So back into here, if I were to flip this thing upside down, then it's the same thing over here. But if I flip this infinite charge upside down, it's still an infinite sea of positive charges. So it should be the same electric field down there, okay? So that's important to understand. And so then what we can do is we can pick, we'll say a cylinder like this. We'll pick a surface like this. Okay. And why do we pick a surface like this? Because I know on the flux on this end here, it's just going to be poking out. And everywhere along here, there's no flux on the side areas. Like the flux is just going to be on the top and the bottom because around here, I made it vertical. See, if I made it at an angle, if I picked a surface that was at an angle, then I'd have some that pierces through the side of that surface, but I don't want to do that. I want to make these sides parallel so that there's no flux going into the side because I know the electric field is only pointing in the vertical direction, right? That's why we got to know the direction of the electric field so we can do that part correctly. So we know the flux is only going to be at the tops and the bottoms here. And this is a cylinder. We've enclosed a certain amount of charge here. I picked a cylinder. Now, it didn't have to be a cylinder. Okay, so cool. Now that we have our shape, now let's do the flux calculation and the enclosed charge calculation. So here is just the electric field, and I picked a distance z down here, by the way, because I know that the magnitude down here is the same. So all of this will have the same electric field. See, if I picked a different location down here, then I'd be like, well, at a different height, it's possible that the electric field be different, right? So I know the electric field, and then the area is going to be the area of these two circles, because that's what the electric flux is passing through, those two surfaces. So let's say I made a shape. Let's say the radius is r. So then this is 2 pi r squared, because that's the area of the circle there. Okay. Now let's look at the charge enclosed. The charge enclosed is this charged right here. Well, that is because it's a surface charge density. It's constant. It's just sigma times the area of the circle, which is pi r squared, right? because this circle has an area as a radius r. Pi r squared is the area times the surface charge density is the charge enclosed. And now let's put these two together. The electric field, the electric flux is equal to the charge enclosed divided by epsilon naught. The pi r squareds cancel, which is good. And so you find the electric field is equal to sigma over 2 epsilon naught, like that. Okay. Now notice a couple of things, kind of interesting. The electric field it doesn't matter on the height, actually. We thought it might matter, but it turns out it doesn't matter. They're just constants, just based on the surface charge density there. Okay. Let's look at another example. We have a long solid cylinder as a radius r carries a volume charge density that depends on the radius, sigma. So this is a volume charge density here, where sigma 0 is a constant, r is a distance from the axes. Use Gauss Law to find the electric field, the distance r from the center of the cylinder, for r less than inside the cylinder and r greater than outside the cylinder. Okay, cool. So this thing is containing a bunch of charge, and we want to know. Now, first step is to understand the direction of the electric field. Now, because it's a cylinder, okay, let's talk about the symmetry here. This is always the tricky part because it's a cylinder. So this piece of masking tape here, or this packaging tape, is going to be my cylinder. So the thing about the electric field is there's rotational symmetry. That is, if I rotate it, it's the exact same charge, right? So there's no way that it could have a horizontal component. Okay. So let's say it had a horizontal component, okay, and you rotated it, right? And you say like, okay, cool, it has a horizontal component. But let's say I flip it around, okay? Then I'm saying that it's actually pointing this way instead. But if I flip the charge around, the cylinder's symmetric, right? So, like, am I saying, let's say I'm saying at the top here, it's pointing at you, right? At this spot, the electric field's pointing at you, right over here. And I flip it around, then I'm saying, well, no, is it pointing at me or pointing at you? You could say, well, it's pointing at you over here and pointing at me over here, but this is like a long charge, right? Like, so there's no reason to think that, let's say I put it in the middle, right? Dead set in the middle, and then I flip it around. Is it pointing at you or is it pointing at me? Right? Because if I flip it around, it's the exact same setup, right? There's nothing special about this side versus that side, right? That's what we mean by symmetry. So there's no reason to think that, so it has to point radially outwards. Like the only way that it can maintain the symmetry if I flip it around is that if it's pointing straight up. So, and it has to have that rotational symmetry too. And so the end result is that we know that the electric field has to be emanating radially outward from this point here, okay, at all of these points. Like if you take a circle of radius r right here, then the electric field has to point radially outward from that. That is to say, if I take a point here, it's radially outward in away from that center axis, right? Okay, so that's, I know it's a little bit tricky. It's going to take some time. You might have to wrestle with that and think about it, right? Think about the reasoning why it couldn't be any other way other than that. Okay, cool. So then now that we know that the direction of the electric field is radially outward because of this uniform charge density, like there's nothing special about it, we're going to then create our Gaussian surface being maybe just a little cylinder right here. Just like make it a little thin. Why? We don't want to be near the ends, right? So we'll just make it really thin. We'll make this distance here, we'll make it like D. D, that's fine. And then the radius is R here. And so then we know the electric field is poking out of this thing like that, right? That's the electric field, and it's uniform radially. Now, I picked the same uniform density because, again, because of the rotational symmetry, the magnitude ought to be the same at the same distance, because if I rotate it, like the charges really haven't changed, okay? So then we're going to say, all right, let's look at the flux. Okay, so the flux is just going to be E times the area here, right? So the electric field, because the same magnitude everywhere, so it's just going to be times the side area here. The side area of a cylinder is equal to the circumference of it times how wide it is, D in this case. Okay, now let's look at the charge enclosed calculation. We have to say, what charge are we enclosing now? And the charge enclosed is anything inside of this little cylinder right here. So any charge in there. Now, this is going to be, as a volume charge density is a function of radius, so we got to find that total charge. Now, because the volume charge density is dependent on the radial, we're going to want to break this, to calculate that total charge, we're going to want to break it into little rings, right? So we're going to make a little ring here, right? it's going to be like a shell, right? A shell, because it needs to be a volume, as being the integral of the dq. And the dq in this case is going to be that little shell of charge. That shell of charge, because go back to the charge enclosed lesson, why we picked the little shell here. We're going to take, and let's say the thickness is dr. So it's going to be the volume, it's going to be the density times whatever the volume of this shell is, right? And we said that that would be the circumference of the circle, right? And times the thickness. And we're going to integrate this from 0 to little r. Actually, I'm going to just change it, make this big R instead, just because I don't want to like confuse the letters here. So I'll make this big R. Big R is the actual point we're interested in, and little r is the variable of integration right here. So that's our charge enclosed. We can pull out the 2 pi sigma naught, and then this becomes r cubed. So then the integral will be r to the 4th over 4, because r squared times r is r cubed. We do power rule from 0 to r. Okay, for little r, so that's 2 pi sigma naught r to the 4th over 4. Those will cancel too, so you get 1/2 pi sigma naught r to the 4th. And so that's the charge enclosed, and then we apply Gauss's law. Equals charge enclosed over epsilon naught. Oh, sorry, 2 pi r. Oh, we didn't do the volume. Dr. Sorry, let me think. It's 2 pi r. I didn't do the height. I forgot the d here, right? So this is the width, length, and then thickness, right? Yeah, so I forgot a d there. So there should be a d in there as well. So then this is going to be E times 2 pi r times the thickness is the enclosed charge, which is 1/2 pi sigma naught r to the 4th d divided by epsilon naught. And that d should cancel. What else cancels? The pi cancels, and one of the r's will cancel, right? So then we solve for the electric field, which is divided by 2. So it's going to be 1/4 sigma naught r cubed over epsilon naught, like that. Okay. Now, how about outside the cylinder? Let's say we picked one out here instead. What's different about this guy right here? Oops, let's make it go behind. Well, the electric field part is the same, right? Because we're still saying it's radially outward because it still has the same symmetry. So that part doesn't change, right? So the electric field, or sorry, the flux calculation, when we do that, is still the same. However, the enclosed charge doesn't extend all the way out to here. It extends only to the maximum R here. Oh, sorry, this should have been, I gotta convert this to, sorry, I know I got it messed up here. This is big R, I'm reusing my letters. So this should be little r. I'll just change this back. Let's just do little r. We'll just forget that the variable here is match, but we're just integrating to 0 r, because in this shell, like, we only went out to little r. We didn't go out to the edge of the sphere. So we'll make those little r again. Sorry if that's confusing on that. It's just I kind of messed up on the variables that we're using. Those are little r, like that. Okay, so the real difference here is when we do the charge enclosed, we're not going to integrate, we're not going to stop at little r, we're going to stop at big R, even though we're closing a bigger, because right now this is my little r, right? It's the distance to a point outside of the cylinder, but we don't have charge in this region. We're only going to integrate up to big R, so it's going to be, the charge enclosed is going to be integral from 0 to big R of sigma naught 2 pi r cubed dr. Okay, so that's going to go to big R as opposed to little r. So that's going to be sigma naught 2 pi. Again, it's going to be r to the 4th over 4. Now with the big R instead of a little r, because we're stopping, the bounds of the integral are only going to stop at the edge of the cylinder, because we're only including the charge after the edge of the cylinder. Outside the cylinder is no more charge, right? So this becomes 1/2 sigma naught pi r to the 4th. But this one is still little r because the circumference of my Gaussian surface shell is still the entire cylinder, right? So then there's a d here. Sorry, I keep forgetting that d. So we're going to set these equal to each other. Well, we divide by epsilon naught. So divide by epsilon naught. And then we can set these two equal to each other. 1/2 sigma naught pi r to the 4th d over epsilon naught. And then we can cancel out the d's. We can cancel out one of the pi's. The r, the big R doesn't cancel. So we just divide by 2r. So it's going to be 1/4 sigma naught big R to the 4th over epsilon naught times r. Okay, so this is for r is less than big R. This is for r greater than big R there. Okay. All right, let's take a look at a sphere. Sphere is the last common shape that has pretty symmetry. This will have radial symmetry, but not from an axis, but because it's a ball sphere, it's going to be radially outward from the center of the sphere. Okay, so we have a total charge there. We want to again find the magnitude of the electric field, R less than big R and R greater than big R in terms of this thing. So it's almost the same setup, but now we're doing a sphere. And this is a uniform charge density, so we don't have a charge density there. But we know that by symmetry, the electric field should be emanating radially outward spherically. So that's why we're going to make a sphere, and then the flux is going to pass outward from the edge of that sphere there. So the flux calculation is just going to be the electric field times the surface area of that sphere. We're going to make that sphere radius little r. Okay, and so that area is going to be 4 pi r squared, which is the surface area of a sphere, because the electric field is going to be the same magnitude radially outward by symmetry, right? Because for a sphere, you can rotate it in all these directions, still the exact same sphere. If I rotate it, it's not like I've actually changed it because it has that symmetry. I rotate it, but it still looks like the same sphere, right? Okay, and then the charge enclosed is going to be a volume charge density. Now, the thing is we only know the total charge. So in this case, this is more of a geometric question. You have to say like, well, it's based on the volume of charge we've enclosed, right? So it's Q times a fraction of the charge, right? And the fraction is the volume of this sphere divided by the volume of that's the proportion. Like if this volume contained half of the volume of the entire sphere, then it would contain half of the exact charge. So we're going to do the ratio of the volumes, and the volume of my sphere here is 4/3 pi r cubed, and the volume of the entire sphere is 4/3 pi big R cubed. So those cancel, so you get it's Q little r cubed over big R cubed. And so now we do Gauss's law, and this is for r less than big R, by the way. So for r less than big R, we're going to have the flux equal to the charge enclosed over epsilon naught, right? That's Gauss's law. So then we can cancel out r squared. This just becomes r, and then divide the 4 pi over. So you get the electric field is going to be QR over 4 pi epsilon naught r cubed, like that. Okay, now what about when r is greater than big R? So now if we take a spherical shell outside of here, what's different? Well, the electric flux calculation is the same. It's still going to be E times 4 pi r squared, but the encharged closed now is just the entire sphere, which contains Q, right? So the enclosed charge is just Q over epsilon naught, right? Remember before, it was just a fraction of the charge because we've only enclosed a portion of the sphere. Now we've enclosed the entire sphere. We get the entire charge, and so the electric field then ends up being Q over 4 pi r squared epsilon naught. And notice a couple of things. Inside the sphere, the electric field grows as you get further away from the sphere, but then outside of it, it drops off 1 over r squared in terms of the dependency on little r, because all the other values are constant. Okay? And so that's kind of like examples of how you apply Gauss's law.